Now that we've explored a bunch of stuff to do with sets, it's time to move on to our next topic, which is relations. And relations are a nice intermediate topic between sets and functions. And we're going to start playing with functions so that we can look at some interesting properties, and so that later on in the course we can get to questions of cardinality, the sizes of sets. And we need functions in order to do that. And in order to need functions, we're going to play with relations, because relations are this nice intermediate object. This is a good place to play around proving things, both for the sake of proving stuff, but also because they're interesting in their own right. Okay, so relations. So many expressions in mathematics describe relationships between different objects. So for example, get my stylus ready here. A equals B tells you that those particular objects are equal. A less than B tells you that the number A is strictly less than the number B. A is an element of B tells you about the membership of an object in a set. A is a subset of B, tells you the relationship between those two sets. One is contained inside the other. And A divides B, tells you that the number A is a divisor of the number B. So these symbols here encode a relationship between the objects on either side of them. And what we do in this topic of relations is we abstract away the details of these things to look at broad and general properties of mathematical relationships between objects. So let's focus on divisibility for the moment, and we can think of this operator, the vertical bar, as being an operator on a pair of integers. So we write A vertical bar B when A divides B, and we write the same symbol now just with a little slash through it to denote A does not divide B. And divisibility on the set of natural numbers naturally defines a subset of n times n. In particular, we can define this subset R, so R is a subset of n times n, to be the set of all ordered pairs A comma B where A divides B. So this will be some infinite subset of n times n. Now, let's dial it back a little bit and just consider divisibility on this set of integers 1, 2, 4, 8. And we can summarize all the relationships, all the divisibility conditions between pairs of elements in the set A with a nice little table like this. So we know 1 divides 1, 1 divides 2, 1 divides 4, so forth. 4 divides 4, 8 divides 8. On the other hand, 2 does not divide 1, 4 does not divide 1, 8 does not divide 4. And so we could summarize things in a table like this. It'd be a little bit cumbersome, and while we can state things that way, it would be nice to be able to express some of these properties back in terms of the things we know about already in this course, namely sets. And so one thing we can do is we can summarize this table as a subset of A times A. And indeed, rather than just summarizing this table as a subset of A times A, we could actually use a subset to define that relation of divisibility. In particular, if I give you this subset of elements, which is just the ones that are successful here, then this table tells you all the pairs where the first thing divides the second thing. So this subset can be used to define the relation rather than just to summarize it. And in that case, we can write, for example, if we pluck out two numbers x and y, we can write x, r, y whenever x, y is in R. And this is supposed to be reminiscent of the notation we saw before, namely say x divides y or x is less than y and so forth. Rather than using a symbol for a particular relationship between objects, I'm going to use R from this subset to denote that relation. And this is supposed to just generalize what we were doing before. So let's summarize some of this stuff in a definition. So if we take a set A, then a relation on A is just a subset of A times A. So we're really abstracting away this idea of a relationship between pairs of objects in saying, well, we're just going to define the relation as being some subset of all the possible pairs. And if a particular pair of elements, x, y, is in this subset, then we write x, r, y. And if it's not, and there's a little bit of an error here in my slides, we write x, r with a stroke through it, y. So for example, we can define the set of just ordered pairs x comma x on the reals. So this will be some subset of r times r. And this is just the relationship of equality on the reals. The only things that are in here are when the first and second elements of that relation are equal, and everything else isn't in there. So this is just equality on the reals. Similarly, we can define subsets x minus y in z, xy in z squared, where we need x minus y to be a positive integer. And if we think about this for a moment, the only things that are in this are pairs of numbers, pairs of integers, where the first one is strictly bigger than the second. And so this is a slightly awkward way of writing the strict greater than relationship as a subset of z times z. Now, in general, for any set, R being the empty set is called the trivial relation on that set, and S being everything, all possible pairs, so B times B, is the universal relation on a set B. So these are always relations we can form, but they're not terribly interesting. So particularly this one is trivial and this one is somehow too much. So one other thing we can do with relations is we can draw the relation, which can be helpful sometimes in certain contexts. So if we consider again this set A and divisibility as the relation, then we can draw a node for each element of A, and if A are B, we can draw an arrow from A to B. Because of course, just because A are B doesn't mean B are A. Just because we have one element, one ordered pair, doesn't mean the reverse is in that relation. So it's definitely not a commuting thing. We'll look at that a little bit later on. So if we summarize things here, we know that 1 divides 1, 1 divides 2, 1 divides 4, and 1 divides 8. 2 divides itself, 2 divides 8 and divides 4, but doesn't divide 1, so we have no arrow back, and so forth. So we get a picture like this. And these pictures later on will be helpful for building a bit of intuition about what relations are doing. Okay, so let's stop there.